Welcome to MOVITRAC LTE-B+ Basic and Intermediate Training. This is Session 3. In our last session, we did a quick startup of our MOVITRAC LTE-B+, and we took a look at the basic things you need to do to get one turning. Now we're going to look at a few more advanced concepts. We're going to explore something called ramps, and we're going to take a look at getting into the extended parameter set. By doing this, we'll be able to change motor control modes and we'll be able to access many additional parameters. Let's get started. I'm going to begin by talking about ramps. Ramps are one of those things that you think should take about 30 seconds to explain, and then the more you get into it, the more you realize it's actually pretty sophisticated. So it's going to take a few minutes to cover ramps, but it's well worth it because ramps significantly affect how your VFD behaves and how it handles your application. So what is a ramp? Put very simply, a ramp is an acceleration or deceleration event. Let me show you an example by showing you a graph that visually portrays what a ramp does. I think you can see why we call them ramps because that's exactly what they look like. The graph you see on your screen is a graph of speed versus time. In other words, the horizontal axis represents time and the vertical axis represents the motor's speed. Now you can see we have a number of things going on here. At the beginning, the motor is at zero speed and its speed increases over a period of time. We call this an acceleration ramp because the drive is speeding up. Then the drive reaches a steady state condition where the speed is constant. The graph is horizontal at that point. And then later the motor starts to slow down. You can see we go into what's called a deceleration ramp as we go from the steady state speed down to zero. So these are acceleration and deceleration events, periods where the speed changes. We specify ramps by entering a time into a parameter in the MOVITRAC LTE-B+, and that time represents the time required to make a 50 Hz frequency change. Now you may wonder why we aren't talking about this in terms of speed, RPM. The answer is frequency is a little more convenient because remember, speed depends on not just the frequency that the VFD is putting out, but the number of poles in the motor. So the same frequency will produce different speeds with different kinds of motors. By specifying the ramp as the time for a frequency change, it makes it a little bit more motor independent. I think this will become a little clearer as we get a little further into this topic. Let's say in this case we set our acceleration time to 1 second and our deceleration time to 2 seconds. What that says is the acceleration ramp takes 1 second to ramp from 0 Hz all the way up to 50 Hz, and the deceleration ramp takes 2 seconds to go from 50 Hz down to 0 Hz. Remember though, the actual speed is going to depend upon the number of poles in the motor. And you probably remember this equation. I showed it to you in an earlier session. It relates the VFD's output frequency and the number of motor poles to the speed in RPM. Let's just say in this case that our motor has 4 poles in it. A 0 to 50 Hz speed change is going to actually be a 0 to 1500 RPM speed change. That's what it calculates out to if you calculate a 4-pole motor. Now that does make reasonable sense, but as we know, there are a variety of motors out there, and also we want to make other kinds of speed changes, so that leads us into the question, what do we do if we want to work out some other speed change? Well, glad you asked, because I have an equation here which kind of gets around all these complications, and here it is. This allows us to calculate the ramp time, which we put into a parameter that will give us the desired acceleration. Let's define these terms and then we'll do an example problem. First of all, speed change. That is the change in RPM that the motor is going to go through. The way we work it out is we take the final speed that you want to wind up at and you subtract the initial speed where you started. And then you take the absolute value. In other words, you don't want a positive or negative sign on it. You just want the change in RPM. All right, that's speed change. Next comes the acceleration time. That's the time you want that speed change to take. In other words, how long it's going to take the motor to accelerate or decelerate through that speed change. And then finally, the outcome of all this is going to be the ramp time. That is the parameter value that gives the acceleration time you're requesting for that particular speed change. In other words, ramp time is what you're going to stick in a parameter, and that parameter will make the MOVITRAC LTE-B+ accelerate through that speed change in the time you've requested. That was a bit of a mouthful. Let's go ahead and look at an example so you can see all this at work. Let's say we want to accelerate a 4-pole motor from 250 RPM to 1000 RPM in 3 seconds. So in other words, our motor is actually already running, but we want to go from a relatively low speed to a higher speed. We want it to take 3 seconds. If we graphed it, it might look something like this. We're ticking along at 250 RPM for a few seconds. Then we enter the acceleration period starting at 3 seconds. The motor increases its speed over a 3-second period, so by the time we reach 6 seconds, we're up to 1000 RPM, and then we're at steady state again for an additional few seconds. All right, that's our graph of our acceleration event. Now we can calculate it using our equation. The first thing we need to do is calculate the speed change. So we take the final speed minus the initial speed, and we take its absolute value. So we take 1000 RPM, which is our terminal speed. We subtract 250 RPM, and that gives us 750 RPM. So that is the change we're trying to initiate with our motor. Notice it doesn't have a sign on it because we've taken the absolute value. All right, now we can use our equation here. So we're going to plug our values in. We'll go ahead and put an acceleration time of 3 seconds in there. We multiply that by 6,000 divided by the speed change, 750 RPM, times the number of motor poles, which is 4. We work all this out, and this gives us a ramp time of 6 seconds. So if we plug that into our MOVITRAC LTE-B+ in the correct parameter, and we accelerate it from 250 to 1000 RPM, it should take 3 seconds. That actually wasn't too hard, and after you've done a few of these, I think this will make sense. All right, so enough math. Where do we put in these values to get these acceleration or deceleration events? Well, we go to a few parameters in the basic parameter set. We set acceleration in parameter 0.3, and we set deceleration in parameter 0.4. Now, by default, these will be set to 5 seconds if you factory default the VFD. That translates to a 5-second acceleration on a 50 Hz motor going from 0 to 50 Hz. But in North America, we tend to use 60 Hz motors, so if you put in a 5-second ramp in these two parameters, it will actually take 6 seconds to accelerate or decelerate a 60 Hz motor, because obviously we've got to go through an extra 10 Hz. If we calculate this out and we assume it's a 4-pole motor, a 60 Hz motor is going to take 6 seconds to accelerate from 0 to 1800 RPM or to decelerate from 1800 RPM to 0 RPM. Okay, not too complicated, but remember we are a European company, so a lot of our products do have that kind of European flavor to them. But anyway, that is where you'll set your ramps in these two parameters. I think it's time to do a hands-on activity, give you a chance to get in here and make a few more changes to parameters. So here's what I'd like you to do. I'd like you to take your motor and accelerate it from 0 to 900 RPM in 1 second, and then decelerate it from 900 RPM to 0 RPM in 4 seconds. So something like this if you graphed it out. 1 second for that up ramp, 4 seconds for the down ramp. And your speed change will go between 0 and 900 RPM or 900 RPM and 0 RPM. So you're going to have to calculate 2 ramps and then go to those parameters, P03 and P04, and put in those numbers. Now, you may be wondering, how can you test this to make sure you're getting the times you want? Well, let me give you a handy tip how to do a little testing. All right, do this. Once you've gotten your parameters entered, fire up your drive by pressing the Start button. Then use the up and down buttons to adjust the speed until you get it to 900 RPM. At that point, hit the Stop button and bring your drive to a halt. Now, get out a stopwatch or the stopwatch app on your phone, start it running, and press the Start button. And as soon as it reaches 900 RPM, look at the time on the stopwatch. That should be 1 second if you did everything right. And then once you've done that, reset your stopwatch, hit the stop button on the VFD, time that, and it should take 4 seconds to come down to 0. So that's an easy way to test it. Preset your speed and then use start and stop to bring the drive up and down. Let me also give you another handy tip. When you're entering large numbers on the VFD, it's really a pain sometimes the way the speed changes as the numbers go up and down the longer you hold down the arrow buttons. Here's something you can try. If you hit the stop button and then press the navigate button, you can set the numbers digit by digit. What this will do is it will change the digit that's activated, so you can move from the ones column to the tens to the 100s to the 1000s. So this is an alternative way of entering numbers. I find it a little quicker when you're dealing with big numbers. Okay, enough talk. Pause the video and do the hands-on. All right, well, I hope that worked well, and I hope your ramps behaved as you expected. Let's go ahead and do a demonstration. So if you don't have your own demo unit, you can see me do it, and if you had problems, maybe this will clear things up for you. The first thing we have to do is calculate our ramp values, and so we're going to do a little math. Remember, we were going to go from 0 to 900 RPM in 1 second, and then decelerate from 900 to 0 RPM in 4 seconds. So we calculate our speed change, and it doesn't matter which one we do, we're going to get the same value. So we take 900 RPM minus 0 RPM and take its absolute value, or we take 0 RPM and subtract 900 RPM. In either case, it's a speed change of 900 RPM. Pretty simple. Now we're going to have to plug this into our equation twice, once for 1 second and once for 4 seconds. So we'll start with 1 second. So we'll take 1 second times 6,000 divided by 900 RPM times 4 poles, and that gives us 1.7 seconds. And then we do it again for 4 seconds. We take 4 seconds times 6,000 divided by 900 RPM times 4 poles, and that gives us 6.7 seconds. So we need to put these values into parameters 0.3 and 0.4, and then test out our drive. So here we go. Let's go ahead and set up the ramps. So what we need to do, of course, first is get into parameter edit mode by holding down the navigate button. Then we navigate to parameter 0.3 and we hit navigate again. And we enter our time, 1.7 seconds. And once we set that, we hit navigate. Then we go to parameter 0.4 and we hit navigate again. And then we enter our second time for our other ramp, 6.7 seconds. We hit navigate again. And that is it. We've entered our 2 parameters. We'll hold down navigate for a few seconds to exit parameter edit mode. And now we're ready to go ahead and test our ramps. So what I'm going to do first of all is get my speed preset. So I'm going to turn DI1 on to enable my drive, and then I'm going to press the start button and then use the up and down buttons to get that speed exactly at 900 RPM. So I'm going to adjust my speed here. Okay, my speed is adjusted. Now I'm going to stop my drive, so I hit stop, let it come down. And then we're going to time our ramps this time. So I'm going to get out my phone and put it on the stopwatch app, and I'm going to hit start, and I'm going to start the stopwatch at the same time, so I'll press both buttons together. Our drive is accelerating, and you can see it got up to speed pretty quickly. After all, it's supposed to happen in 1 second. And my time worked out fine, so I'm going to reset my stopwatch, and I'm going to hit the stop button and start the stopwatch at the same time. And we'll check the down ramp. Let's do that. Okay, and now we're coming down. And that took about 4 seconds. So it looks like we have been successful. All right, so that's acceleration and deceleration. It's very important to set this correctly for every application. It's going to be very application specific. Many application problems can stem from improperly set ramps, so this is definitely an area that your skill and experience comes to bear. But we are done with ramps for now. Let's move on to our next topic, and that is extended parameter mode. Everything we've done so far has dealt with just the first 14 parameters in the parameter set. But as I told you in an earlier session, there are actually 116 parameters. By default, most of them are hidden. It's just done so that people don't get confused and overwhelmed by so many parameters. But if you're going to do anything other than very basic operations with your MOVITRAC LTE-B+, you do need to get into the more advanced parameters. So we're going to look into unlocking the full parameter tree. We unlock the parameter tree by going to parameter 14 in the basic parameters, and we change it from its default value to 101, which is kind of like a password to unlock the extended parameters. We go in there and we edit that parameter in the basic list, and as soon as we do that, a whole bunch of additional parameters will become accessible. You can now go past parameter 14 to 15 and on and on and on. So here's what the full parameter tree looks like. It has 116 parameters total. The basic parameters are the first 14. They're used for essential configuration. Then we have what are called the extended parameters. There's 52 of these. They allow you to do additional configuration tasks, including some advanced things. And there's also then a group called the P00 parameters, of which there are 50. These are all read-only. You can't change them. They are status parameters. They tell you information about the VFD. And this can be extremely helpful when you're trying to troubleshoot a problem or perform some kind of diagnostic task. We will look at the P00 parameters later on. We won't be covering them here, but be aware the parameter tree divides up into these three categories: basic, extended, and P00. Okay, well, now that we understand how to get into the extended parameters, we're going to take a look at some additional concepts that work with those parameters. So you had to know how to get into them before we could move on. We're going to move on now by talking about a topic called stops. Stopping the VFD. Now you're probably thinking, well, stops are pretty simple, aren't they? The VFD just shuts off the power and the motor comes to a halt. Well, yes, that is true. However, stops are actually much more sophisticated, and the VFD has lots of different ways it can stop itself. So let's talk about stop modes, how the VFD comes to a halt. The MOVITRAC LTE-B+ can stop the motor in 3 different ways. The first is called coast to stop. That's a very simple stop mode, and as you can guess, the VFD just basically switches power off and then the motor coasts until it comes to a halt by friction. The second mode is called ramp to a stop. In this case, the VFD deliberately slows down the motor at a very predictable speed and then brings it to a halt. And then there's something called rapid ramp to a stop, which is pretty much the same idea, except it happens very quickly. Let's talk about these characteristics in a little more depth. It's very important that you understand how each one works. In some cases, you can select how the VFD will behave, and it's very important to pick the right mode. All right, with coast to a stop, this is sometimes called an uncontrolled stop. The VFD just cuts off the power transistors, and then it just waits for the motor to come to a stop on its own. Now, this might happen very quickly. If the motor doesn't have a huge load on it, probably friction will bring it to a stop in just a few seconds. On the other hand, if you've got a very large load with a lot of momentum, that motor may turn for a long time before things come to a halt. So for this reason, the stop time isn't known. It's dependent on a lot of different factors, such as the size of the load, the friction in the system, and the configuration of the application. Now, if you've got a brake on your motor, you can bring it to a stop pretty quickly because the brake will apply as soon as all this happens, and the load will probably stop very rapidly. But if you don't have a brake on the motor, it's very application dependent. So be aware of this. Ramp to a stop is a little different. The VFD deliberately uses parameter 04 to decelerate the drive at a predictable rate. Then, when it's reached the end of the ramp, it turns off the transistors. What that means is you actually have a very predictable stop time. You know how long it will take. If you've got a brake on the motor, it will get applied near the end. If you don't, it's still probably not a problem since you've deliberately slowed down and stopped. Rapid ramp to a stop works exactly the same way, but it uses a different parameter to get the ramp value. It goes to parameter 24, which is in the extended parameter set, and it's usually set to a very short value, so you get a quick deceleration. So that is rapid ramp to a stop. P05 in the basic parameter set selects the stop mode, and you can set it to 3 values. You can set it to 0, 1, or 2. If you set it to 0, it's going to ramp to a stop using the ramp in P04. If you set it to 1, it will go into that coast to a stop mode. And if you set it to 2, it will also use the ramp in P04. So there's no difference between 0 and 2. You may wonder, why is this duplicated? You'll understand in just a minute, so just hold that thought. The rapid stop ramp lives in P24, which is in the extended parameters, so you have to unlock the extended parameters if you wish to set this value. It defaults to 2 seconds, which is fairly quick. It's intended for situations where you need to stop the motor more rapidly than normal, so you usually set it to a fairly short value. What kind of events can trigger a stop? Actually, there are quite a few. Pressing the stop button on the VFD's keypad is one possibility. Another is input changes. The digital and analog inputs can change in a way that would trigger a stop. You can send a command over a field bus to the VFD if it's being controlled by a PLC or other industrial controller, and you can request a stop. And then faults and errors often cause a stop as well, because something goes wrong and the VFD halts itself when they occur. Stop behaviors may be fixed or configurable. What that means is some stops you can pick what kind you want. You want them to coast to a stop, or do a ramp, or a rapid ramp. On the other hand, some stops are hardwired to do one specific thing. For example, some just do a rapid stop, and that is the only choice you get. Or some just do a coast to stop, and that's all you get. We'll talk about these as we go along. Now we're going to talk about a related topic to stops, and that is how the MOVITRAC LTE-B Plus responds to power failures. What I'm talking about here are situations where the main power fails completely. Now you might be thinking, well, if that happens, doesn't the motor just stop? Don't forget, the MOVITRAC LTE-B Plus has filter capacitors which are charged up, and the motor is going to actually keep operating on these for a limited period of time. So it is within this window that the VFD has the opportunity to decide how to handle the power failure. As it turns out, there are actually 3 different ways that the MOVITRAC LTE-B Plus can handle this, and it's your choice which one it is. The first one is write it out. In other words, don't do anything, just hope the power comes back in time before the capacitors go flat. The second one, which is similar to the way an ordinary stop is handled, is coast to a stop. In other words, shut the VFD output stage off and just let the motor coast. And then the third possibility is do a deliberate rapid ramp to a stop. So what will happen in a write it out situation is the VFD will reduce the motor's speed, but it will attempt to keep running using the energy in the capacitors. Now, if the power comes back quickly enough, then this will work. It'll come back up to speed and all will be well. But the outcome is ultimately unknown. It really just depends how long the power is down. If the power is down too long, eventually the capacitors will run out of energy and the motor is just going to go into coast mode. So this is okay if you expect that power will come back, that it'll just be a short blip, but if it's too long, you could get in trouble. Coast to a stop deliberately turns off the transistors as soon as the mains drop, and then it allows the motor to coast, and eventually it will stop. Again, though, like the other coast to stop we talked about, it's ultimately unknown how long it's going to take to stop, because that's dependent upon the load, the application, friction, and several other factors. The third possibility is the most controlled outcome, and what will happen is the VFD will use the deceleration ramp stored in parameter 24, and it will deliberately try to bring the drive to a controlled stop using the energy in the capacitors. If it succeeds in doing this, it will then turn off the transistors and all will be well. Of course, how long you've set the ramp is going to affect what happens. If there's enough energy to get you all the way through it, all will be well. But if you set P24 too long, then you may actually wind up coasting at the end. So it depends. How do you set power failure responses? Well, very interestingly, you use exactly the same parameter that you use to set stop responses. You use parameter 05 in the basic parameters. So this one kind of does double duty. If you put a 0 in here, it's going to ride it out if a failure happens. If you put a 1 in there, it will coast. And if you put a 2 in there, it will use parameter 24 and attempt to ramp to a stop. This brings up a very natural question. Since parameter 05 is kind of doing double duty, how are you going to handle both stops and power failures? Well, you have these possible combinations. If you put a 0 in there in stop mode, you'll ramp using parameter 04 and you'll ride it out if there's a failure. If you put a 1 in there, it will coast to a stop in all situations, both stop mode and power failure. And if you put a 2 in there, it will ramp to a stop using parameter 4 in stop mode, and it will do a rapid ramp to a stop using parameter 24 if there's a power failure. This explains why in stop mode 0 and 2 are duplicated modes, because this allows you to get 2 different power responses, and that is why they did that duplication. But clearly, some combinations just aren't possible, so you have to pick the combination that works best for your application. And that is all I have to say about stops and power failures. We now move on to a new topic, and that is more advanced motor control. I mentioned in one of the early sessions that the MOVITRAC LTE-B Plus can control a variety of motors, and that it has 2 asynchronous motor controls, VF, which we've already explored during quick startup, and a more advanced mode called LVFC. So we're going to talk about how to switch to LVFC mode. By the way, it stands for Light Vector Flux Control. It is a more advanced mode that gives better speed control and generally better overall stability than VF mode. The way it does this, it simulates closed-loop feedback by calculating what the motor is doing. It is still an open-loop control system. There's no motor encoder involved, but it kind of simulates one, and it does a pretty good job simulating it. And that enables the VFD to have better control. So, in general, if possible, I recommend using LVFC mode. You would mostly use VF mode if you just couldn't get the motor to work quite as well in LVFC mode. And of course, don't forget, if you have a MOVITRAC LTE-B, the older version, you don't have LVFC mode, you only have VF mode. So how do you change to it? It's very simple. First of all, you should confirm that the motor is disabled, because you need to have that off when you're going to change the motor control mode. So DI1 should be switched off or unjumpered. Then do a standard quick startup by setting the motor voltage, current, frequency, and speed. Pick the control mode you want to use, in other words, whether you wish keypad or terminal or field bus control. Then set the motor's maximum and minimum speeds and set the 2 speed ramps. So basically do everything you need to do in the basic parameter group. Then unlock the extended parameters by putting a 101 in parameter 14 and go to parameter 51, which selects the motor control mode, and change it to 0. It will be 1 if you do a standard quick startup, which is VF mode. Change it to 0, that is LVFC mode. And then the VFD needs to do something special. It needs to do something called auto-tuning. What the VFD does, it puts some current through the motor's windings, it takes some measurements, and then it makes some adjustments to parameters. Auto-tuning is not available in VF mode. This is something LVFC mode requires, and it optimizes the VFD to the motor's characteristics. Now, the way you trigger this is relatively simple. You just have to set a parameter, but before we talk about that, I want to give you a warning. The motor may move during auto-tuning. So be sure you've taken appropriate safety precautions before you enable auto-tuning. In other words, the motor must be able to run, and it must be able to run safely. It may or may not move, so just consider the possibility that it could. So here's how we trigger auto-tuning. We go to parameter 52 and we set it to 1, and as soon as you do that, auto-tuning will begin. You'll hear the motor make some funny noises and possibly move. This can take up to 2 minutes. Eventually, however, it will be complete, and then the VFD is going to be tuned to the motor and able to operate in LVFC mode. Okay, so that is all you have to do to change modes. What I'm going to talk about next is not unique to LVFC mode. It applies to any motor control mode, but this is a good place to talk about it. And that is setting the pulse width modulation frequency. If you remember, a few sessions ago, we talked about how PWM generates a synthetic alternating current that controls the motor by varying that frequency across the range between 0 and a maximum value. What I didn't talk about when I introduced PWM is the base PWM frequency, what is sometimes called the modulation frequency. Now, the PWM generates a variable frequency to control the motor's speed, but the pulses it's sending out that create that synthetic AC occur at a fixed rate. This is called the modulation frequency. It's a fairly high frequency, so these pulses turn on and off very rapidly. The VFD can vary what the modulation frequency is. Now, you may wonder, why do you care about this? Why does it do this? It's very simple. These are the modulation frequencies available. It can do it at 2 kilohertz, that's 2,000 pulses per second, and it can go all the way up to 16 kilohertz, which is 16,000 pulses per second. It turns out that at the low frequencies, the VFD runs cooler, but it is rather noisy. You can actually hear the modulation frequency coming through from the motor. It's kind of a high-pitched noise. Some people find it very irritating. As the frequency goes up, the motor gets hotter, but it also gets quieter, because most people can't hear those high frequencies. So generally, when you pick the modulation frequency, you're picking it for the application. If you're working in an environment where quiet is important, for example, if you have a VFD in a theater operation, maybe where it's controlling stage machinery, you would want to use the highest modulation frequency since very few people can hear those. But you would also have to accept the fact your VFD might run hotter, and you might actually have to have a slightly larger size one to be able to handle the situation if you're running near its upper limit. On the other hand, if you're in a factory environment that's already very noisy, you could use the lower modulation frequency and have the VFD run cooler. And so that is why you can set it, so you can optimize it for the application. So to set the modulation frequency, you go to parameter 17 and you put a number in it. This sets the maximum PWM frequency, and these are the numbers. Notice I said that P17 sets the maximum PWM frequency. That is because the VFD is intelligent, and if it starts getting too warm, what the VFD will do is it will automatically start dropping the frequency lower and lower until the temperature situation optimizes. All right, so I think it's time to put all this into practice. Let's have another hands-on. Here's what I'm going to ask you to do. It's got really simple instructions. You've already done a quick startup, so your VFD is already ready to run. You just have to make a few changes to do these things. I'd like you to switch to LVFC mode, do the auto-tuning, and then change the pulse width modulation frequency to 16 kilohertz because it will have defaulted to 4, so up it to that highest frequency to make it inaudible. So go ahead now, pause the video, and do the hands-on. All right, well, I hope that went well for you. I'm now going to demonstrate how to do this, so let's go ahead and do a quick demonstration. All right, now to change to LVFC mode, we need to unlock the extended parameters. So what I'm going to do first is I'm going to hold down the navigate button a few seconds to enter parameter edit mode. Now I'm going to navigate to parameter 14, so I'm going to move to that one, and I'm going to change that to 101. So I hit navigate, I set it to 101. And I hit navigate again. That unlocks my extended parameters. You notice now I can go past parameter 14. So I go ahead to parameter 51. And I hit navigate. You can see it's set to 1 right now, which is VF mode. I'm going to change it to 0 and hit navigate again. And that completes changing to LVFC mode. We need to tune our motor. Now this is a demo unit, so it's perfectly safe if the motor runs, but I am going to just remind myself that it could run, so I'm not touching it or anything, just to be safe. I'm going to move ahead to the next parameter, parameter 52. and I'm going to put a 1 in there, and as soon as I hit navigate, the VFD is going to start tuning. So my motor will make some funny noises and it might move. I hit navigate. All right, well that is auto tuning completed. So now we need to change the PWM frequency. So we go to parameter 17. And we're to change it from 4 kilohertz to 16, and I hit navigate. And those are all the changes I have to make. So I've done everything required. I hold navigate down for a few seconds to exit parameter edit mode. And now it's time to run the motor. I'm going to switch my enable on, so DI1 is turned on, and I'm going to hit the start button on the VFD, and it's going to go back to whatever it was running before, which was actually 900 RPM, so I'll just let it ramp up, and that seems fine. I'll bring it to a stop now, let it ramp down. And that seems fine. So we have successfully changed to LVFC mode, and I no longer can hear the noise the motor was making. So that means my PWM is changed. All right, mission accomplished. And that is the end of session 3. In our next session, we're going to look at how to connect to the MOVITRAC LTE-B Plus using a PC, and we're going to get into using the engineering software LT Shell. We're going to do this because it allows us to work with the parameters more conveniently, and also it gives us a few extra tools to do some more powerful tasks. See you next time.